Hello, my dears. Here we will continue with the transient response. In the previous lecture, we talked about the first order and the second order. Here we are going to go to the detail of the second order. As I mentioned in the previous lecture, the second order response need more detail to be studied. So here we are going to start with them. So the transfer function of the second order system is having this format. It seems to me like this format is not giving us enough information about the response. That's why we need to rewrite the the transfer function in general, in different way, which is going to give us more information about the response. Like this format, we will write it as a GS equal to omega n square over s square plus 2 zeta omega n s omega n square. Of course, I think it's very clear. You notice that B here is written as omega n, and then A is given here as a 2 zeta omega n. So A equal to 2 zeta omega n, B equal to omega n square. Omega n is defined as the natural frequency or the frequency of oscillation. We remember the response, something like this. So there is oscillation. So this frequency of this oscillation is known as natural frequency, or it's omega n. And zeta is defined as the damping ratio. This zeta is the damping ratio. How the response is damping, how the response is damped toward the steady state response. Example, find zeta and omega n and the transfer function gs equal to 36 over s squared plus 4.2s plus 36. So simply we will write it like this: omega n squared equal to 36, which means omega n equal to 6, because root of 36 is 6. 2 zeta omega n equal to 4.2. We will substitute omega n here. We will find that zeta equal to 0.35. So second order response as a function of damping ratio. If I want to consider the system or represent the system in terms of the damping ratio, I want damping ratio to tell me something here. So if the response is having this format, we'll find that the poles of the system can be written, the pole for this system can be written as minus zeta omega n plus minus omega n under root square of zeta square minus 1. So that's how we can write the pole of that kind of system. So we are talking about the two pole because second order, so it's going to be S1 and S2. So he write both S1 and S2. So once it's going to be minus zeta omega n plus omega n under root square of zeta square minus 1. The other one will be minus zeta omega n minus omega n under root square of zeta square minus 1. Now if I want to relate zeta to the responses which we studied in the previous lecture, you will find that if zeta equal to 0, the system will be undamped. The system is undamped, and the poles are going to be only imaginary value, and the response is going to look like this. System is undamped. So zeta is telling me about the response. The other thing, if zeta between 0 and 1 means zeta more than 0 and less than 1, we are going to consider the system as underdamped, and its poles going to be real and imaginary, complex. The response is going to have this shape. When zeta equal to 1, it's a critical damp, because if zeta equal to 1, that means we are going to have the two poles in the same location, and the response is going to look like this. When zeta greater than 1 or zeta more than 1, it means the two poles are located at real axis, and its response is having this shape. Example, for the system shown, find the value of zeta and report the kind of response expected. Means we need to calculate zeta, and from zeta we must be able to know what kind of system we have. So we will calculate zeta as omega n square equal to 12. Fine, then that means omega n equal to root 12. 2 zeta omega n equal to 8, 2 zeta omega n equal to 8, as you see here. So omega n calculated earlier as a root square 12, substitute, calculate zeta, you will find that zeta is 1.155, which means zeta is more than 1. If zeta more than 1, we are going to know, or the system is known to us as overdamped. The other case, if we have this one, of course, we will start by calculating omega n. Omega n squared equal to 16. Omega n squared equal to 16, as you see here, which means from there we'll find omega n equal to 4. Now, 2 zeta omega n equal to 8. This 8. 2 zeta omega n equal to 8. From there, omega n is known as a 4. We will substitute it here and rearrange to find zeta equal to 1. Zeta equal to 1 means the system is a critical damp. Now this is the general format for the second order response. As I said, most of the system is most of the response is going to be underdamped, which having complex quantity. So this is the general format for underdamped. From there we are going to find the same definition as before. The definition will come in the next slides, where we are going to find, for example, time rise. We know it. Time rise is the time taken from 10% to 90% of the response. We will have settling time. Settling time is the time taken until the response go within 2% of the final value. Notice here the 2% are clearly shown. This is the final value. 2% means 1.02 or 0.98. That means if this is the final value, this is plus 2%, this is minus 2%. As long as the system oscillating within these 2%, we will consider the system is entering to the steady state. So at the first time they enter to this boundary, which is going to be here, we are going to call this one settling time. Also, there is another time expressed here, which time TP, the peak time, which is the time taken until the response goes to the highest value in the response. We call it TP. C max, the maximum value in the response. C final is the final value of which is the steady state. That's how we can define the second order response. So here he gave me TP, the peak time, which the time required to reach to the first or the maximum peak, the first peak or the maximum peak of the response, which to be calculated as pi over omega n and the root square of 1 minus zeta square. Percentage of overshoot is giving me some information about how high the response, how high the maximum value goes as compared to the final value. Let's say this is the final value. How high the response as compared to this one. So this data can be figured out by the percentage of overshoot. He said here the amount of the wave overshoot the steady state or final value at the peak time, usually expressed in percentage. How to calculate it? We calculate it here in terms of C max minus C final over C final into 100. C max means this point. C final is the final value. Okay, multiplied into 100%, you will get the percentage of overshoot. Or we can calculate in terms of zeta. So it's equal to exponential of minus zeta pi over root square 1 minus zeta square, all into 100%. So you can calculate it either this exponential into 100% or this ratio into 100%. Also, we can use this equation to calculate zeta. If we have the overshoot and we need to calculate zeta, we can calculate zeta as minus ln of percentage of overshoot over 100 divided by under root square of pi square minus ln square of percentage of overshoot over 100. So this is how to calculate zeta if you have the percentage of overshoot. Settling time, as we mentioned earlier, is the time required to enter within plus minus 2% of the final value, and is to be evaluated as 4 over zeta omega n. So the settling time is to be calculated here as 4 over zeta omega n. At rise time, which the time taken to go for the response to go from 10% to 90% of the final value, which to be calculated from this equation. Time rise is going to be this one. This is time rise. So if I can calculate it, but this is approximate actually, this is approximate kind of equation. From here we can calculate TR as this value divided by omega n. Consider this example. He said find TP, percentage of overshoot, TS. TP is the peak time, percentage of overshoot, and settling time, given the transfer function of the system as, so this is the transfer function. We need to calculate these elements, the equation given earlier. So we will find, first of all, I need omega n and zeta as usual. So omega n square equal to 100. From there we find omega n equal to 10. 2 zeta omega n equal to 15. From there we calculate zeta as a 0.75. The system is underdamped. Now I can calculate TP as a pi over omega n under root square of 1 minus zeta square. Substitute omega n and zeta, you will find the time is 0.4. And percentage of overshoot, since I have zeta, we can calculate the percentage of overshoot using zeta from this equation. Exponential of minus zeta pi over root square of 1 minus zeta square into 100. We calculated to find that it's 2.8%. 2.8%. Settling time is 4 over zeta omega n. Zeta is given or calculated. Omega n is calculated. You will find it's equal to 0.533. Now we will evaluate some of the given definitions from the location of poles on S-plan. I mean, graphically, we will evaluate it. So if you look at the pole location, you will find that there is a pole located at this point, where this pole is having real part and imaginary part. What is the value of real part and imaginary part? We will look at omega d as a damped frequency of oscillation, which to be calculated as omega n root of 1 minus zeta square, which what is this? Actually, this is the imaginary value of the response, of the pole, the imaginary value of the pole. So the imaginary is known as the damped frequency and is to be calculated as omega n under root square of 1 minus zeta square. Sigma d is the exponential damp frequency, which is known as zeta omega n. Zeta omega n is the real value. This is the zeta omega n. Now I realize that by understanding or by catching the real part of the pole and the imaginary part of the pole, we can calculate some of the parameters. TP calculated earlier to be pi over omega n under root square of 1 minus zeta square, which means we can write it as pi over omega d. So now I know that TP equal to pi over omega d, and TS equal to 4 over zeta omega n, which means we can calculate TS as a 4 over sigma d. Remember, this is the imaginary and this is the real of the value of S. One more thing also from the figure we can realize is the value of zeta. If you look at zeta, zeta is equal to this part. If you look at this one, zeta omega n, this one, if I divide it by omega n, this is the value of omega n. If you divide this value by this value, it will give me actually cosine of this angle, which means if you divide them, they are going to, this part cancel with this part will give me zeta. That means cosine theta equal to zeta. That's what you want to tell us. So the angle theta, which can be calculated as zeta omega n over omega n, is actually give me the value of zeta, which means zeta is cosine of that angle. Zeta is cosine of that angle. Let us consider these observations from the graphical representation shown in the previous slide. He's saying here that TP is inversely proportional to omega d, this one, which the imaginary part of the response, and Ts is inversely proportional with sigma d, which is the real part. So he said inversely proportional means once omega d increased, Tp will decrease. He wanted to teach us here something on how can I control those parameters, how can I control those times. So if I want to shorten Tp, now I know what to do. If I want to shorten Ts, I know what to do in the response. I know how mathematically this can be done. The other thing he said here, since horizontal lines on the S-plan are line of constant imaginary value, they are also line constant of Tp. So we will consider Tp is affected by the imaginary part. That's what he wanted to say. And similarly, Ts is affected by the real quantity, as he mentioned here. And this one is affected by, or Tp is affected by the imaginary value. Another observation here, since cosine theta equal to zeta, radial line are line of constant damping ratio zeta. What he want to say here, he said, if let us take this position, for example, this position. If I draw this line, we are going to get cosine of this angle is equal to zeta. So it's very clear that the damping here higher than the damping for the other one. The bigger the angle here, the bigger zeta. The bigger the angle, the bigger zeta, because cosine of the angle is going to get greater, so zeta is going to be bigger. Okay, that's the idea he wants to say. So if with this condition we will get, or with this angle we will get zeta is small, which means the damping will be faster. If you compare it with this one, zeta is bigger, which means damping will take longer time. Let us go to the extreme. The extreme, I will take it with this angle. If the angle is equal to 90, what will be the situation? System is undamped. Undamped. It will never damp because zeta is equal to unity at that time. So system will never damp. The other observation here, he said, since percentage of overshoot is only function of zeta, radial line are thus line of constant of percentage of overshoot. So the same thing. You notice here, percentage of overshoot is affected by zeta. So if zeta is increasing, percentage of overshoot will increase. That's the point. So we are having percentage of overshoot at this location and different percentage of overshoot with this function, with this location. What he mean by these locations? Let's say I'm going to take, for example, this is the location of the pole, or this is the location of the pole. Or maybe somebody would say this is the location of the pole and this is the other location of the pole. So if I want to compare between them, I will find, let's take this one. I will assume, I will take this one, this pole, this point here, and this point. If we consider these two, you are going to find with this one, zeta is smaller. With this one, I mean, with this one, zeta is smaller, percentage of overshoot will be smaller. If I go to the other one here, zeta will be bigger and the percentage of overshoot will be bigger. So that's how we can decide from the location of the pole how the response is going to look like. From the from the location of the pole, whether the real part is bigger or imaginary part is bigger, or there is no real part or only imaginary part. This is all going to tell us something about the values zeta or percentage of overshoot. Here he gives us some information about how the change of the location will help me to figure out the response in different way. What he mean by this? Let us consider three cases. In this case, we will find that the pole location will change in terms of imaginary value. Means the imaginary value will be 1. Real value is here. This is the real value. Now let us look at the imaginary value. We will change only imaginary value to see how this is going to affect the response. So we will consider case number 1. At case number 1, it gives me the response, this one. So how about if I change the position to 0.2? I mean, the real is the same, but imaginary, I change it to 0.2. We are going to get this kind of response. How about 0.3? If I go to 0.3, which this point here, how the situation going to look like? You are going to get this response. What is the difference between one and the other? I hope you can see them clearly. If you look at them clearly, you will find the frequency of oscillation is going to get higher as we are increasing the value of imaginary, or the imaginary value increased. The damping will be faster if the value of the imaginary is smaller. That's how we can evaluate. So you will find that the change of the position will affect some of the parameter, damping ratio, percentage of overshoot. It will affect also the frequency of oscillation, all going to be affected by the change of the imaginary value. How about the real value? If I keep the imaginary here, let us keep the imaginary at this position and change the real value to position 1, and then after that position 2. If we are at position 1, we are going to get this response. It's very clear now. What will I get there? I will get the frequency is the same. Frequency of oscillation is the same, but the percentage of overshoot is affected. Also, settling time will be affected. Settling time will be affected. So these are how, or that's how the parameter can change as the real quantity change. Similarly for this case, third case, what if we change both? So we are going to get some changes in some of the parameters. So he wants to tell us something here, that you can play with the position of the poles and zeros, especially poles. We can play with the position of pole. What I mean by position, if I want to control some parameters, we can change the real value. Other parameter need to change the imaginary value. Other parameter, maybe you need to change the real and the imaginary value. That's how the response is going to be affected by the change of the poles of the second order system.